Hey everyone, welcome to second semester. First semester was just dealing with slopes and rates of change, and second semester is pretty much the reverse, and that is area. So we're going to start off nice and slow with estimating area. So if you take a look at your notes, section 1, you are driving in your car and your velocity in feet per second is going to be plotted versus time, which is going to be measured in seconds. How far did you travel over the first 80 seconds? So we're talking about from time 0 all the way until time 80 seconds. And you know from a long time ago that distance equals rate times time. And we can approximate by finding the area under the curve because our time is on the x-axis and our rate is on the y-axis. Between t equals 40 and t equals 80 seconds, our velocity is pretty much constant at 60 feet per second. So this region right in here, I'm using my little highlighter, okay, we can estimate the area of that just by finding the area of each of these boxes. And the distance traveled within that time interval right here, distance equals rate times time. The distance traveled would be our rate of 60 feet per second. And our time from just the from just the 40 until the 80 is going to be 40 seconds. Okay, so this is only for that highlighted region. If you multiply this out, seconds are going to cancel and you're going to be left with a unit of feet, and this is going to end up being 2,400 feet that you traveled just in the time from t equals 40 until t equals 80. T equals 40 to 80. Okay, and that's only part of the story though, because we were asking how much over the entire time. Here's a little bit of a problem. This region is going to be very difficult to figure out the area because the rate of change, our velocity in feet per second, is no longer constant. And if you look at it, it's curved. And the only way that we could do this is to figure, maybe we could estimate it. We can maybe count the boxes, or perhaps estimate this with a circle or a quarter of ellipse, or maybe even a trapezoid. But either way, this is just going to be an approximation. So for this little region right in here, oops, hold on. We can only approximate, for now anyways. Okay, so that's what this lesson is going to be on, how to approximate area if our rate of change is no longer constant. This process of evaluating the product in which one factor varies is called finding a definite integral. So anytime that you are evaluating a product, if one of those factors is varying, is going to be called a definite integral. Okay, so that's what a definite integral is. If we look at a function in a generic sense of the term, let's say we have a function f of x and our x-axis is just labeled as x. We don't have any units on this one. And if we wanted to find the definite integral of this function from x equals a until x equals b, so this region right in here, and you're trying to find the definite integral, which is the product. So this distance in here is pretty much our base, okay? And we could find the area by multiplying base times height, but the problem is, again, our height is changing. It's not constant. So that process is called the definite integral. So I think that's my favorite thing about calculus is we take something really simple like area and then we make it look really difficult by calling it a definite integral of a function f of x over an interval of x from a to b. So go ahead and hit pause, copy that down, and absorb it. I think one of the things that people had mentioned last semester is they were writing stuff down, but they weren't taking time to process. So after you write it down, look back over this and reread it and write down any questions that you have. So it's important to look at the word estimating here, because the entire time that we're looking at the area under the curve, for right now until we learn some more techniques, we're just estimating that area or that definite integral. One of the techniques that we're going to be looking at is just counting squares on a grid, as basic as that sounds. So take a look at the first example. We've got a velocity function v of t defined by the equation shown. When it asks us to estimate the definite integral, that means find the area. So we're looking at from the time interval starting at 0 and going to 1. So we're looking from 0 all the way until t equals 1. So the area under this curve is the definite integral of the function v of t from from time equals 0 to time equals 1. Okay, so that's what we're looking for. So this first technique is as simple as counting boxes. And it seems a little tedious, and it is a little tedious, and there's no way around it. One of the ways to do a little shortcut here is by kind of dividing this up into regions. Because we are estimating, you can do this any way that you want to. I'm going to take a look at that region, and I can count full boxes. And we're going to count this region, and we're going to count, oops, that goes all the way over to there. Count the number of full boxes in that one. It looks like I could go up to about there, and there's full boxes in this guy, and same thing here, and same thing here. Okay, so let's go ahead and count the number of full boxes, and then you are going to do your best to estimate by counting portions of boxes about how many you think there are. So I'm going to give you a couple minutes, hit pause, and see how many boxes you come up with. No, I'm serious. Actually hit pause and go count the number of boxes. This is the easiest assignment I'm going to give you, so go do it. All right. I got 108. You could have had 104. You could have had 110. You could have had 112. The idea is that you have something around that number. If you got something like 90 or 80 or 170, you're a little bit off. The next thing that you need to do in order to estimate is look at the dimensions of the box. And this is something that we love to mess you up on as teachers and as AP people. The devil's in the details, as they always say. So if you look at one box that you counted, the bottom portion, here's my little squiggle, has a dimension of 0.1 seconds. Okay, so again, if you look back at your picture, you see me, I'm darkening just one little box here. So that's what I'm blowing up here. All right, so it has a dimension of 0.1 seconds on the bottom. It has a dimension going up of 2, and the units here are going to be inches per second because that's what our y-axis is measured in. So overall, if you multiply the base times the height, the seconds are going to cancel again, and you're going to have 0.2, sorry, this is kind of hard to do in here, 0.2 inches as a dimension of one box. So if you want to estimate the value of the definite integral, the area under the curve from t equals 0 until t equals 1, just take your number of boxes, times the dimensions. All right, so I got 108 boxes that I counted, times the dimension of 0.2 inches, and that gives me 21.6 inches. So that is the definite integral for this function. So take a look at the second example. Estimate the definite integral, so we are estimating area under the curve, of the function f of x equals 1/2 x squared plus 1. Our x values, our starting value is 1, our ending value is 4. There are a couple things that you need to be able to do on your calculator in order for you to proceed with this semester. We're using our calculators much more this time around. So one of the things that you need to be able to do is auto scale. If you don't know how to auto scale, there's going to be some links that I put up on the website for you to go and do on your own, but it's something that you got to be able to do. So regardless of the model of calculator that you have. So if you don't know how to auto scale, go ahead and press pause on this video right now. Go to my link on my website and figure out how to do that, and then come on back. So even though we could graph this function by hand, we're going to let our calculator do it for us, and we're going to auto scale. I like to always start my x value a little bit less than my starting x value over the interval, and end it a little bit further beyond the interval that we are going to be estimating, because it helps to put it in the window a little bit better. So if I auto scale from 0 to 5, I'm a little bit easier to see this picture. So I'm getting a graph that looks something like this. Forgive me, I know it goes through here, and it's going to go through about here, and I'm going to sketch this as best I can. And I know it comes back down and goes like that. Okay, well, that's the best I can do for now. Another thing I want you to be able to do is turn on your grid. Okay, the grid is going to give you exactly what I show here. It's going to give you grid lines so that you can count the boxes. And have your X grid have dimensions of 0.5. And your Y grid is going to have dimensions of 1, so that it matches up with my diagram. Okay. Again, because we're estimating, it doesn't really matter what you make your grid as long as you can count boxes, because that's what this whole part is about. So we're going from 1 until 4, and you're just going to count up all the boxes. So go ahead and hit pause. Count the number of boxes that you think you have, and just like we did in the example above, go ahead and figure out the dimensions of the box and multiply those two numbers together and see what you got for a definite integral. All right, well, I counted 24 blocks or boxes, and each of those had a dimension of 0.5. There's no units on this one. So I am getting a definite integral value of 12. That is the approximate area under the curve from x equals 1 until x equals 4. And that's about all for the lesson. So again, auto scale, putting on your grid, counting boxes, and multiplying numbers together. That has been the lesson to estimate area. Talk to you next time. Bye.